Hey boys and girls, this is Mr. Senval, and here we are with homework video number 7 for 8th grade, Parkways, and we're going to be thinking about Newton's laws. We've been talking about that a little bit, but now we're going to kind of lay them out for you. So make sure you have your journal ready. If you don't have your journal, have a piece of paper and make sure that you write all of the notes as we go through the video so you can get full credit. Make them neat and complete. All right. Okay, so we've been talking about motion, and we know these are a lot of terms we've been using in class recently, potential energy and kinetic energy. And all matter is in motion, so we're trying to describe it because it affects us. We're always in motion, and the world is in motion, and our galaxy, our solar system is in motion, so this is very important to us. We've been talking about energy, and energy, all matter, all stuff has energy. Energy is what we need to do work, to move things, to put things into motion. We need energy, and energy can be transferred, as you see here. The sun heats up the atmosphere and the land, creating wind, which can cause those wind turbines to spin and then generate electricity, which could be used to charge up a battery in a car. And now the car can move throughout the world, and it all started with the sun. So we know energy is moving around. Another way to think of energy, again, a review, is that energy can destroy or damage things, as you see in all these pictures here that we talked about in last week's video. So energy has the ability to cause damage. When you can think of what has more energy is what would cause more damage. There's electrical energy, heat, chemical, atomic, potential, kinetic, so there's different forms of energy. Energy can transfer and take different forms. Now let's review real quick on potential energy and kinetic energy, okay, because we've been talking about that in class. Remember, potential energy is sort of like stored energy. It's energy that has the capacity to turn into some other form of energy. And there's three kinds, okay? There's elastic potential energy. Now that's when you squeeze or stretch something like a rubber band, right? When you're stretching it, you're giving it a lot of potential energy, and when you let go, it will fly pretty fast. It could hurt, could cause some damage. So that's elastic energy. So, and also the same way if you squeeze something. If you squeeze something, it has a lot of energy like that spring there, it will expand. We've talked a lot about gravitational potential energy. The higher you go up, the more energy you have because gravity is pulling you down. And you see in this picture, the blue skier is higher up on a bigger ski ramp, so he has more energy because he's at a greater height, right? He would be moving faster and at the bottom of the ramp faster than the red skier there. So that's gravitational potential energy. That just depends like where you are off of the ground. And we've talked a lot about examples in class, like the guy on the ladder, the people falling through the chair, and what have we, and the house of cards, for example. So that's gravitational potential energy. And then there's chemical energy. So matter has energy just in the chemicals in the molecules, like food, right? There's the food, that pasta with this hungry kid, it's not really doing anything, but if we eat it, there's energy in there that our cells can use and then our muscles can use to move us. So that's chemical potential energy. Another example is gasoline or fuel, right? Just sitting in your car with your car turned off, it's not doing anything, but it has potential. In the chemicals of that fuel, of that gasoline, there is potential to be able to turn your car, get your car going and get your car moving, all right? So when we think about our models and our diagrams in class, think about potential energy. Is it elastic, gravitational, or chemical potential energy? Especially like the car crash test. Those cars were on the ground and they had a lot of kinetic energy, but they also had a lot of potential energy, chemical potential energy in those gas tanks, right? Okay. Now, potential energy can turn into kinetic energy, the energy of movement, right? When motion, it's released and things move, and you have an arrow flying from a bow and arrow, or some object rolling down a hill, as you see the cyclist, or your muscles moving, or a car moving. These are all matter, objects in motion. They had potential and now it's turning into motion. Okay, kinetic energy. So in your notes, okay, let's get ready, pencil ready. Write down again your own definitions for potential and kinetic energy. All right. And now we're going to talk about Newton's laws, okay? So write down in the left-hand column Newton's laws, and then skip a couple lines for first, second, and third, because there's 3 laws. And I want you to write notes in your own words explaining like what these mean, okay? What these mean to you and how something that would help you remember and understand these, okay? And Newton's laws, Isaac Newton, famous guy in the 1600s, scientist, and he described how matter moves, and he came up with these 3 laws that help us understand how things are in motion. All right, and remember, let's review what a force is. It's any push or pull, and it can cause an object to move faster, move slower, or stop, or change direction. And so without forces, things wouldn't move, right? Pushes or pulls. Okay, so Newton's first law, it takes a force to move an object, or it takes a force to change an object that's already moving. Basically, it's saying things don't move unless you give it a force. It'll just stay there. And if something is moving, it will stay moving forever in whatever direction it's going, unless a force changes it or stops it. So, right, a soccer ball sitting on the field is just going to sit there. Its gravity's pulling it down, but the ground is also pushing it up, so it's stuck in balance, and it's not going to move unless somebody comes and kicks it, okay, and gives it a greater force than what it already has. So that's Newton's first law, and that's pretty basic, right? It makes sense, right? So the soccer ball's gonna, if you kick it, and then the soccer ball will not stop unless it hits something else, and you see there, it will eventually stop if someone else kicks it, or if it hits the net in the back of the goal, and then that will stop it. So it needs another force to stop it. All right, and we talked about in space, since there's no friction and there might be no gravity if you're far from a planet or something. So something's moving in space. Like we have these deep space probes that are like just so like actually exiting our solar system now, and they're just going straight at the same speed, and they'll go forever unless they run into something, because there's no air, there's no friction, no gravity. So they're just moving, and they're never going to stop. And because there's no force to stop them out in the middle of interstellar space where there's really nothing, just open space and no air, no friction, nothing. All right. Okay, so write something for that. You may need to pause. Newton's second law is that formula, force equals mass times acceleration. So basically it says a force is an acceleration on a mass. So bigger things that are more massive, they need more force to get them moving. And if you give an object more force, it will accelerate increasingly, okay? So you could kick a soccer ball, maybe a little tap pass to somebody, or maybe you're going for a penalty kick and you're going to kick that soccer ball a lot harder. So the more force, that ball is going to accelerate, it's going to move and speed up faster, okay? And that kind of makes sense. Just like this, if you had to push a big ball or a box or something, the bigger the mass, you need to push it harder. The smaller, it's easier to push. Think about our skiers, the father and son. If they were skiing down the hill at you really fast, the little kid would need less force to slow him down, and the father would need a lot more force. And if they ran into something, the little kid's not going to knock it over a little bit, and the dad, if it ran into you, it might hurt a lot more. So more mass needs more force, and the harder you push something, it goes harder. And we'll talk about that more in class. Okay, Newton's third law. Again, pause, process. Think about the first and the second law. Okay. Third law, ready? Every force has an equal and opposite force, or every action has an equal and opposite reaction. Forces come in pairs. Remember, we've talked about this in class. So if you fall down, so you're sitting in the chair, right? The chair's holding you up, you're pushing on the chair, it's all balanced, two forces pushing against each other. But if something breaks, now the gravitational force pulling you down, your weight is going to crunch the chair, because now it's not equal. But then you'll hit the floor, and now again you're balanced. The floor is pushing up on you, as the same as you're pushing on the floor. Same thing with kicking a soccer ball. When you kick the ball is actually putting a force on your foot. And now you might be thinking, it doesn't really, I don't feel anything. I just kick the ball and it goes really far. But if you were to kick it barefooted and maybe just straight with your toe, it would probably hurt. That's because the ball is pushing back on your toe just like you're pushing on the ball, and the harder you kick it, the more it's going to hurt, right? So equal and opposite forces. Now think about it this way. If you were trying to kick a bowling ball, that would definitely hurt. So that bowling ball is putting a lot bigger force on your foot as you kick it, directly in relation to how hard you're kicking it. So you would not want to just go slam a bowling ball with your foot because that would hurt. So that's Newton's third law right there. So everything has an equal and opposite action or reaction or force. Think about it this way too. When a rocket shoots off in the sky, the exhaust is shooting backwards, but the rocket then pushes forward. So there's a great example of Newton's third law. The fire and fuel is going out the back, and the rocket moves forward. They're going opposite, equal and opposite. Okay. All right. So potential, kinetic, Newton's first, second, and third laws. Write down some notes to help you remember that, and then draw a picture, a diagram to also help you think about Newton's laws. All right, make that picture neat. Don't just draw, a ball and then leave it like that. Use some arrows, use some diagrams. Show me something happening. Show some movement. Okay. All right. Thanks for watching homework video 7. And remember, when you're in class, any class, when you're at school, anywhere in life, are you above the line or below the line? Sometimes we go below the line. Let's remember, let's go above the line, own our actions, take responsibility, and find solutions. All right, thanks for watching. We'll see you soon. Bye.